Hello, it's July 2nd, 2023. What I hope today is to kind of get figured out from this book of Kazarnoff from Yale University Press, what is about geometric inequalities and describing the arithmetic mean and the geometric mean, which we've kind of discussed, figure out what is the harmonic mean, and then to discuss these things kind of variously. So we've been talking about the arithmetic mean, or the average. So you sum n different items, or many different items, and many different items, and then you divide it as that many times. You modularly divide it by n, or split it off in that each time that when you split it off the first time, it's 1/nth. And you split it off the next time, it's 1n minus 1th. And you split it off the next time, it's 1n minus 2nd. Now, is this the same thing as just dividing it by n? Well, not necessarily, no, because when you're kind of figuring out what are the pairwise operations, otherwise it's a summary and it's an aggregate function, or what? It's kind of as an analytic function, but an aggregate function. It's a sum that then when you divide it by so, it's kind of taking for so many sums, so many divisions or portions. About how there's a general discussion here for arithmetic proper, that everybody's provided with the laws of arithmetic, addition and subtraction, multiplication and division, for numbers regularly, and they're getting with various representations of numbers like integers and fractions and rational numbers and irrational numbers and real numbers, decimals and decimals with infinitely many places, or irrational numbers or rational numbers. And then they also with inequalities and these other properties of the trichotomous real numbers. And so then there's some consideration that these have a deconstructive account. And so really it's possible to divide it up even finer in a sense and have addition after increment. Increment is just adding one. Increment and addition, multiplication and powers, exponent and tetration. And then it's similar for this division, that it admits a kind of more primitive operation, which is that you know you're going to divide something so many times, and so then you take off that part of a portion and that part of a portion, that part of a portion again. So it's implemented just by subtraction, just like multiplication is implemented by repeated addition. That given the operand, that its results that it's a bit more of a is it a more fundamental operation? That's basically the point, is that it's a more fundamental operation. And so that in accordance with this kind of approach, it makes it possible to consider how to define that for addition and division as these opposite sides now, instead of addition and multiplication going out and their inverses coming back, that they come together in the middle, this idea of addition and division. So this is a kind of one of these kinds of approaches that's been taken generally in these talks, which is the deconstructive accounts, and really reaching towards what could be the ways to look at, and given that we have some of the baggage that's accumulated over time since antiquity, since before there was called even a negative number, or there's no negative quantities, before there were imaginary numbers, before there were negative quantities, before there was division even so much, and that there was only, it started with tally marks, making counts of things, and the increment and addition and this and that it results a way to then even approach the very formalization that's given today as the piano's numbers, Giuseppe Piano's the successor function, which is like increment, and then figuring out how that makes modularly addition, and then multiplication that really kind of even demands that it has this complement with the addition and division together to even define arithmetic at all correctly. That otherwise what's left is that real analysis, and has to eventually, after it figures out least upper bound and a completeness of the density to make real numbers continuous in a continuous domain, or that they have the property of gaplessness, it's called completeness, that then defining measure 1.0 at the very end is kind of off-putting, because otherwise what represents in the model these integers don't really reflect that they go to infinity, because they could just be stacked up between some zero and some finite number and just incrementally just fill up a space less and less and less each time. It doesn't really establish, without otherwise this notion of measure, arithmetic formally and from foundations. So for that being a pretty elementary concept, that these are still the same rules and laws of the numbers that so follow all the usual interpretations of counts and the numbering of things, that still it represents that from the logical view, where everything has to be utterly well defined, and eventually that there's no generosity in saying, well, I see what you mean by that, so even though you haven't explained it, it's appreciated that I get what you meant, ... that these formal conscientious mathematical logicians with their rigor cannot allow their mathematical conscience to accept that, because that's fundamentally illogical. I'm not sure if it would generally be put across that way, but that's what it would be. And so there's no room for generosity in conscientious mathematical formalism and constructivism. And so figuring out these kinds of things is both elementary and of a kind of like learn some things even from reading this book, which is geared towards secondary students, about inequalities and the geometric mean and the arithmetic mean so far. But there's other things that represent that mathematics writ large kind of needs to have a revisiting of these things, because what was long ago left behind as a fait accompli, and an action that is done, is not done. And so then the idea is that for these other notions of completeness, then for example after the complete order of fields completeness, there's this line continuity and signal continuity, that without same it would be again bereft of a certain generally available for the conscientious mathematician and the professional mathematician and the amateur mathematician and the logician, these factors and aspects of its reality, that without same it's missing out, it's bereft of these things. And so that is a criticism leveled at formalists writ large is kind of speaks to this joke. There's a joke about these mathematical formalists, and it says formalists are formalists 6 days a week, and on Sundays they rest, or something like that. But a conscientious formalist is a formalist 24/7, and so it's not allowed either A, to reject what are mathematical objects, nor B, to declare they have what they don't, and nor C, to follow from contradiction anything at all, except the existence of said contradiction. So after the arithmetic mean, it's an average. And so the idea here is to figure out how that when things are summed together, because the proofs that have been built up about it are as well these pairwise proofs. It's like I can establish for the first two, then it's like so, and then one left will be the minimum maximum, and shuffle those out and bring those on down. And so it's pairwise, the approach for inductive, that then for however many there are, it's satisfied and revolves around or rolls back up for these things. So then the idea to re-explain division, instead of as the usual notion that you can just make a fraction of as a denominator, a recounter, or whatever you want to call it, of the numerator, that instead that's actually defined recursively as built up from these other operations, then about how that would be made to define it in terms of only 1 over a number and then subtracting those out, just kind of like repeated addition as multiplication, that this repeated subtraction of this varying quantity is division. And so the geometric mean is kind of similar. You take the product, you multiply all these things together, any number of different values, and then by that same value, you take that root of it. And so it's similar then to figure out what's this kind of inverse operation or modular increment, say, operation for taking the root and the powers, like would be so. When you take a power, you can think of that something to the nth power is it times itself, times itself, times itself, dot, 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 till it's done. And that's its usual representation, that 2 to the third power is 2 times 2 times 2. Now, when you want to take the third root, it's not, it's what so equals that the quantity to its third power equals this thing. And then there's the law of roots about that's basically taking one third, and for the third root is the number to the 1/3 power, and it happens to be that's what works out what it is. So similarly for the arithmetic mean and the geometric mean, and other properties where there's the product one way, and then in terms of one of these other scale linear terms like addition and division for the arithmetic mean, multiplication and that has powers then and roots for this geometric mean. You can see that it's arithmetic addition, and then for multiplication it's next, division is what results in arithmetic mean. And for the geometric mean, you can see that it's taken the multiplication and power, it's what's next, taking its inverse root, which is its next mean. And then it has these properties about how it equalizes and centralizes and brings all this stuff together. That then the similar kind of notion is to take this, what would be next after incremental multiplication, taking the exponent of something, and then taking this inverse tetration of it, making another kind of mean. And observing that it would have similar sorts of results about this log linear type business, and how that results in making stuff into the means. So here there's been discussion basically of trying to find what's the middle where things go about the origin. So when you have a polynomial, take its derivatives, eventually they go flat and go to 0. When you have the negative powers and you take their integrals, eventually they get up to 1 over x and then ln x, and negative x ln x. And they come back in a different way. And the idea is to figure out how that scale factor applies to that, so that then you can figure out how it runs seamlessly and gaplessly above and below the origin to make for what's here called the stop derivative or the stopping derivative. That the idea being that then you can employ what's the methods of the operator calculus and things like the indexicality, or that its order and rank is a range and doesn't stop at 0 from the one way and stop at 0 from the other way. That how they meet in the middle and have the bridge is to define a set of functions for this kind of thing. So it's not so dissimilar for the means, and building this up just as simply an analog from these lesser functions and these factors and pieces of arithmetic to arrive at an abstraction of the very definition as after the operation. Anything of this similar kind of framing is having the same properties after all. And where they're different, that they're mathematics, that they're objects of mathematics, and then they have mathematical properties. Then to find formulas, identities, equations that bridge them, that find where the branches join, that figure out where the things live, that make it so that they're actual, then they're real. These are the kinds of things that are underexplored in mathematics, but could be very fruitful and help very much establish the continuing act of the deconstructive account called abstraction that makes it possible for mathematical thinking to then be able to apply abstraction to things and get above this stuff. So that's kind of was my thinking about it, because I was a little bit wondering about my understanding of the arithmetic mean and geometric mean, after refreshing some familiarity with the definitions, then there's lots to be made for the properties. And when those become part of the toolkit grab bag of methods and analysis, then eventually one will have the fate of that. Given any mathematical problem, it's only the next tool that comes out of the toolkit that is available. When you have a hammer, everything's a nail. But when you can't, when the toolkit grab bag is arbitrary, then everything is whatever it comes out of the bag. It's a hammer. And so here, then the idea is to figure out then if it's going to be in terms of arithmetic and number theory, all I want to put in this toolkit grab bag are things that basically make it so that you can arrive the other parts of the mathematics from it. So the idea is to make those suitably abstract, yet suitably concrete and well-defined and well-posed, I say, if not necessarily in the sense of Hadamard, but well-posed, that it results that there's enough of the basic fundamental abstraction so that everything fits together. It really is a hammer. And so these are the sorts of things that are part of my approach in terms of the lever, the hammer or the lever. So here's this Zernoff's Arithmetic and Geometric Means, Chapter 2. Here's the dog ear. If there was someone who did not have an intuitive grasp of the concept of distance between points on a straight line, then the preceding marks could be used to define the concept for him. See, this is just an example of something that, without another meter or measure or yardstick, that this is an example of the differences of absolute quantities that does. This was the end of the last reading. And then he notes that, for example, when you have these inequalities and they express relations between elements of a domain when they're totally ordered, and then that when you introduce absolute quantity and take out of those, that those flip meanings for positive and negative numbers, and then that with regards to in the inequalities, those that can sometimes be written as multiples of these sequences of inequalities or systems of equations, systems of inequalities, systems of inequations. These reflect kind of what I was just describing about the abstraction, the suitability, and the, if not interchangeability, the reflection that is a comprehensive whole. That these are the kinds of things get into it. So the next chapter is chapter 2, and it's titled Isoperimetric Theorems. Iso, same, perimeter, circumference, or outer length, theorems, proofs, models, or formulas which so establish relation. So we talked about how he talked about finding, when we were talking about the rectangular and the circle, why the circle of the shapes has the most area for its perimeter, and then that for regular polygons have the most shape given that they have so many sides of their perimeter. And then there was the example for the square, and then the square took advantage of a different particular fact to establish that squares among rectangles have the most area for their perimeter, because when you get off the when you take when you take a number and you take its square, those times 4 are the most value that there can be, that any other numbers that factor the area and then adding up as if they were 2 sides apiece would be less. We got into that discussion. Then the other idea was to take that in extremis, and here it means infinite, and so you take the square and then you flatten it to a rectangle that's 10 times as wide and 1/10 as high. And you continue that till it's infinity wide and infinitesimal high. Then the idea was, then in accords with his notions of vitality and the doubling space, that again has this area the same, and then that whether its perimeter is really that its perimeter is definitely more than its area. That it, as its perimeter goes to infinity, still its area stays the same, and that this got into then some discussion about the doubling space and about how when it is so, that its area equals 2. That's a real thing. That is a proper account of its analytical character, its measurable character, its area is a thing. So that otherwise we get back to reading from the book here. The problem which you met in section 1.2 of determining the rectangle smallest perimeter among all those with area 1 is but one of the problems of maxima and minima in geometry. Problems of this kind were studied by Greek geometers before the birth of Christ. Of course, it is uncertain who were the first people to pose problems involving maxima and minimum, but many arise quite naturally and might yet occur to people in a primitive culture. For example, what is there about the shape of a circular cylinder that causes many flower stems, tree trunks, and many other natural objects to take its shape? Why are small water droplets and bubbles that float in air approximately spherical, and why does a herd of reindeer form a circle if attacked by wolves? Admittedly, these problems involve mathematics only indirectly, but they are capable of stimulating mathematical thought. There are problems which are more directly mathematical. For example, what shape should a plot of ground be so that a given length of fence will enclose the greatest area? And what are the dimensions of a cylindrical container so that it will contain the greatest volume for a given surface area? Can you think of other examples? The Greeks were mostly interested in natural phenomena, such as the hexagonal arrangement of cells in honeycomb, but they also had practical problems. Many were connected with war, just as in our day, such as the problem of estimating the size of an enemy's camp. One would not like to be in the enemy's neighborhood at dawn with too few men. The assumption was that the number of men was roughly proportional to the area covered by their camp. It was common to assume the measure or size of an enemy's camp by the length of its perimeter. Often this procedure gave misleading conclusions, and hence a better, more mathematical solution to the problem was sought. Mathematical questions underlying many examples cited above are of two kinds: of all geometric figures having a certain property, which has the greatest area or volume, and of all figures having a certain property, which has the least perimeter or surface area. Loosely speaking, both these problems are called isoperimetric problems. Isoperimetric means with the same parameter. The famous isoperimetric theorem, which took mankind over 2,000 years to prove after it was discovered, gives a solution to a broad class of these questions. Theorem 9, isoperimetric theorem. A, of all plane figures with a given parameter, the circle has the greatest area. Why? Because it has the least angles in it. Yet it still has curvature. Right? Now that not that leads directly to the notion that that it's infinite. It has infinitely many sides, or that has infinitely many angles. This circle as a regular shape, two-dimensional shape. Here it's just a fact, as is mentioned before. So what I mentioned before, that's called the isoperimetric theorem. Okay. B, of all plane figures with a given area, the circle has the least perimeter. Same. In language appropriate to three-dimensional space, this theorem becomes: of all solids with a given surface area, the sphere has the greatest volume. Of all solids with a given volume, the sphere has the least surface area. One way I think of this is about the spiral space-filling curve. What's the spiral space-filling curve? Well, it's a spiral, so it's non-crossing, and it's ever increasing its distance from the origin as it's drawn out. And so that kind of defines that it has to be a spiral, because it never loops back. Because otherwise you can imagine a space-filling curve that's just like folding and going back and forth and whatnot. Any way you can scribble a dot, any way you can fill it on the page, it could be like so. But this spiral is an outward spiral from the origin, and it's like so. So it's space-filling, which means it leaves no empty space as it goes out. And then it's a curve because it's either a curve or a line. So here it's a curve. Then the idea is that the reason the isoperimetric theorem holds is because all the volume is in that for any perimeter at all. Then that to make any other shape like a square or triangle, it's like you end up taking basically the line is the shortest distance out of the spiral after it's drawn. So the spiral exists first, like a Descartes vortex or a disk, a unit disk, or the entire plane filled with one of these things. And then a straight line goes out of that. And so the reason why the isoperimetric theorem holds is because in this setting, it's just a property of that all the area is already inside. And so to get a perimeter out of it at all, any of these other polygons is outside that and has to draw extra perimeter. So this is one way to approach it. In this chapter, we shall discuss several isoperimetric theorems. We shall begin with some simple ones and conclude with a discussion of the isoperimetric theorem itself. First, permit me to mention a little of the history of this illustrious theorem. The solution of the isoperimetric problem for rectangles is already known to Euclid. A solution, he says the solution, but it's not necessarily something the solution as presented. Perhaps the solution as is well known. Even the idea of the formula for a triangle's area is space times height over 2 is so well known because it's built up usually with reflection from parallelogons and then half of one of those, base times height over 2, where base times height is area of a parallelogon. Instead, even the very idea is one of these things about the rigorous formalism in mathematics is how is it even arrived at? How is it even so? How can it possibly be? It's a thing, and so for a long time it's like so, and then what gets adopted as a prescribed solution is itself what it is, but there are others is that otherwise what would be uniqueness results need to be established, and then that those are almost always distinctness results. The solution, or a solution of the isoperimetric problem for rectangles is already known to Euclid. Euclid is most famous for Euclid's elements and Euclid's geometry, and he was a guy. But then his books were the result of a panel and about 50 or 100 years of research, and then it was called Euclid. And so he had input, and he wrote some of it. It's a panel. Who lived about 300 BC, and is probably known long before, as many of the theorems in Euclid's Elements are not Euclid's original work. Archimedes, one of the greatest mathematicians of all time, knew the statement of the isoperimetric theorem. One of the big studies in the 20th century was called soap bubbles. So Robbins and Courant are both pretty great, and they studied how it is that in 3 dimensions, and for arbitrary wireframe shapes, that a soap bubble will naturally assume the shape with the least area, that surface tension naturally draws it together to make this. So when they needed to compute something, it would be possible to just kind of like make a shape corresponding like so, puts a soap bubble of a particular known tension and density and its properties, measure the particular amount, how that was of it, code it, and like so. It's similar to this one experiment that we did in chemistry in a long time ago in the high school chemistry class. We had a lab. It was lab chemistry. And what you did is you have a pool of like oleic acid or something like that, and you needed to measure how much floated up in the system, but there's no way to really differentiate it. So what you do is sprinkle on like this pine or it was pollen, and so it had a very fine character and a very measurable intensity. So then what you ended up finding was then you could plot out the area on the top of the container, and then basically draw a grid and then count how many grids were filled up with the visible evidence of this indicator, and then use that to compute the area of the slick. And so that's similar with these other kinds of analog computers or scopes. indicators and what these methods of experiment make for making these things kind of like so. So, anyways, after there's Archimedes knew the isoperimetric theorem, and there's lots of ways to approach it as like why a balloon is round mostly, all of their shapes, or these kinds of things, because then it gets into the conservation laws and the tendency of what's called the principle of least action, that these systems automatically minimize the one quantity for the other because they have nothing to do but not alter that. By the beginning of the Christian era, the study of maxima and minima in geometry had considerably advanced. We know, in fact, that Zenodoros, who lived sometime between 200 BC and 90 AD, wrote a book entitled Isoperimetric Figures. These are unfortunately no copies of his book left for us to read, but his results were described and proved again by Pappus of Alexandria, who lived about 300 AD. Yeah, I was looking at Pappus's hexagonal theorem the other day, and it's dual. And it's pretty interesting about how the points basically make a bracket after a Kuratowski graph for the midpoint, where the intersections of the lines connecting those points, any 3 points on any two lines, on any 3 points on both of any two lines, connecting all those together, where they intersect happens to be collinear, those 3 points. Why, and then for his complementary dual, that 3 lines coming into a point, 3 lines coming into another point, drawing across from those makes another. So that's but Pappus has a variety of theorems that are named for him, and then also reminds me of the 9-point theorem about when you have 3 triangles. 3 circles in a triangle, or 3 triangles in about a circle in a larger triangle, or the circle in the triangle, and the 9-point theorem is a pretty interesting thing. And as to why they don't apply so much to like 4 points on a line and dot 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 is a specific feature relevant to figuring these things out. So anyways, Pappus of Alexandria, who lived about 300 AD, CE. We do have copies of his book, Pappus de Alexandrie, La Collection Mathématique, Book 5, edited by P. Verrecke, Brouwer, Paris, 1933. Pappus, of course, knew the isoperimetric theorem, and what is more interesting, thought he had a proof of the theorem that a circle has greater area than any polygon with the same perimeter. In the main, his work is exact and easy to follow. Little progress was made from the work of the Greek geometers until that of Simon Lhuillier, a Swiss of the late 18th century, and of his fellow countryman Jacob Steiner, 1796 to 1863, after him. The methods developed by Lhuillier and Steiner in their research have had great influence on mathematics and are still being used. Methods of Steiner were essentially geometric rather than algebraic or analytic. That is, synthetic methods. In other words, he reasoned from the geometrical properties of figures without resorting to theorems of algebra and calculus and methods of analytic geometry. In analysis or calculus, you often set up things in terms of related rates. And then for minimization and maximization is to express things in terms of the derivative integral and then solve for zeros as local minima, and then various tests for what are local and global minima. In other words, you used or are using synthetic methods in your study of plane geometry. Through his methods, Steiner solved many problems which had resisted solution even with the help of the calculus invented by Newton and Leibniz in the 17th century. Here the author puts invented in quotes because mathematics is discovered, and so notation is written and it's adapted and it's shared and it's common, and so but then it's again discovered that its relations. So mathematics is discovered, especially for Platonists who have that already exists, independent of our meager, humble existence. It's always there for anybody. In turn, Steiner's work stimulated growth in analytical mathematics, especially the calculus of variations. So for finite differences in the integral calculus and then the umbral calculus and the calculus of variations is a thing. And it's its own kind of thing. And then for the Yenri, there's a bunch of different fields that basically make up a sensible, fungible, tractable milieu for a calculus, and that which calculates, and these sorts forms then which make for differential geometry, or linearizations, or approximations, what are called numerical methods. So, and especially when they have closed forms and they're exact and make for what they do and are perfect. So these are what we call calculi, and so here he's mentioned one that I need to study some more, the calculus of variations, and relate that to Giancarlo Rota's umbral calculus, methods of finite differences, Newton cotes, and such. This was because of the error in his proofs of the isoperimetric theorem. The error was found by the German mathematician Karl Weierstrass, the founder of the rigor characteristic of modern mathematics. So Weierstrass is usually held up in very high regard as who put his foot down and said, this is the way that real analysis is justified. Prove me wrong, or I'll prove you wrong. So Weierstrass is with Cauchy, that modern analysis is after Cauchy-Weierstrass. It's formalisms. And then there was Riemann, and then we have axiomatic set theory way down beneath, which holds it up. There's also the spiral space-filling curve, which is another way to go about getting to there. So, in order to fill the gap in Steiner's proofs, Weierstrass had to develop the calculus further. Now, one thing we'd been talking about sometime when we were still studying the Fourier book, and about Gonzalez Velasco's historical account of Gauss, Riemann, Dirichlet, and Lebesgue. And about Dirichlet and Poincaré, what was going on with in terms of everywhere discontinuous and those kinds of things. So, as a brief aside, what I wanted to discuss was that the arithmetic mean is always greater than the geometric mean. But if you imagine where Euclid's line is straight and smooth, and Poincaré's line is straight and rough, because it's as if where it was almost everywhere discontinuous, and according to Dirichlet, it kind of came together. So this is one of these prototypes of how a continuous domain exists, vis-a-vis pointwise removable discontinuities, and the piecewise it's all added up back together. And these notions of the everywhere discontinuous functions and the signal continuity and the Dirichlet function and this kind of thing. It's basically two approaches to what is a straight line, and is it smooth because it's actually kind of if it's just kind of drawn out, or is it rough as is actually that's his final crumple that is rough. And what's the ordering of the real numbers, and what about the vague fugue of the real numbers and this kind of stuff. So anyways, the idea is that the arithmetic mean and the geometric mean are equal when they're unity, specifically, or when the numbers are equal, a little less generally. And so the idea is that when it's a Poincaré rough, that the geometric and arithmetic exchange also about the rough too. It's as where it's Poincaré mean rough. Now, this is using loaded terms, and so one always wants to avoid the loaded terms that already have meaning, and that mean has a meaning, and rough has a meaning, but they're reflect these otherwise, that they're ideal quantities just as these are other ideal quantities, and that words in mathematics are neither good nor bad, but we do try to select them and keep them, that they are generally not reflective of bad things in society that would distract or that otherwise that take away from the instructional experience or the learning experience or anything else to do with it. So anyways, Poincaré's rough lines about the everywhere discontinuous and Euclid's smooth planes about the smoothly continuous. It's also after, there's a fellow named John Bell, 20th century. He's got smooth infinitesimal analysis, which is, again, an attempt to get a bunch of these considerations since antiquity that Cauchy and Weierstrass had put a kibosh on because the mathematics needs rigor to be sound, that these are the kinds of things then back into this descriptive count where the geometric mean could be above the arithmetic mean, or they would share the line, and it wouldn't be determinate which one came first in terms of the ordering and the vague fugue and some of these other concepts that are present in descriptions of mathematical objects, a continuum. So the idea about that is what I wanted to mention. And then that also gets into about when we talk about the when we were talking about the Fourier style, and it was established that it converges in a bounded region. Then outside that region, it could diverge. Then the other idea is about the arithmetic and geometric mean, that there are considerations of windowing boxing which would make it so where that something like the arithmetic mean outside some bounded region in a Fourier style analysis would diverge, where the geometric one would not. It would have less tendency or propensity to do so. And similarly, when the units are natural, as in between 0 and 1, and then there's also a way to think about, well, then powers would suffice to make this inverse mean between 0 and 1 in that case. A geometric anti-mean or something like that. That the invention of these brief phrases to denote these general systems just reflects inversions and alternatives in the operators that exist, then that they exist by their mere expression, then that their properties to be so established is what's called making a development. So Lhuillier, Steiner, isoperimetric theorem, Weierstrass. He had to put the whole subject upon a rigorous, logically sound basis. Steiner's work possesses a great deal of charm. I have tried to conduct a discussion of this chapter in the spirit of Steiner and to illustrate his methods at every opportunity. Isoperimetric theorems for triangles. Now, I'd like to skip ahead and see what I can find out about the harmonic mean, because besides the fact that there's described here a class of means to construct means, then famous for history since antiquity are the arithmetic mean, the geometric mean, and the harmonic mean. And then all these other scale, projection, linear means that I just invented or discovered, which have yet to have much development. They're underexplored, and thus it's not really clear if they're fungible, tractable, applying to other aspects of mathematics, but they surely are. Is that I'd like to get to the harmonic mean and get back to a little bit more differential analysis in the talks. Isoperimetric theorems for triangles, equilateral, regular, always regular. It happens to be the least perimeter for the most area. Frames inequalities, and then it's like so. Sets up a case for contradiction. Thus D is exterior, which he had that he was making a point. He drew some lines internal to the triangle, and so that according to an inequality, that according to his synthetic development, that this point would not be interior to the triangle unless it was so that they're equilateral and angles. And so consequently, TABC is greater than TABD, where that about the interiors and exteriors, that is like so. Before we go on to the second proof, let us agree on some notation recall a theorem from plane geometry. Once for all, let us agree that if ABC is a triangle, then ABC denote the lengths of its sides, namely A is the length opposite, or length is the line connecting B and C, and B is the line connecting C and A, and C is the line connecting A and B. Also, let us agree that P is its perimeter, as T is its area. So he says Heron's theorem, Heron, Heron, or Heron. For any triangle ABC, 16t squared equals this quantity, A plus B quantity squared minus C squared times this quantity, C squared minus this quantity, A minus B squared. And so that gets into the parallelogon and base time height times 2, and about 4t squared, that being the area, and then to square that both ways, and bringing that back down is about those 4 sides, and then that over 2. He sets up h is the length of the altitude, height, expresses that about Pythagoras. The area of a triangle is half the product of the lengths of the base and the altitude, using this theorem, and b squared minus e squared for h squared. So there's ideas about what happens when that collapses. Does that arithmetic and algebraic relation still hold up? One or the other, both? Question is maybe. And the answer is maybe. And it does be induction, and when it goes to 0, where it's undefined, as one or the other of the sides is infinite, and then it's usually framed that it's 0 because one of the other sides is infinitesimal, and the only standard infinitesimal is 0. So he just plugs in these numbers and writes them out and factors and collects like terms, and then takes roots and then factors that back out, and he arrives back at this expression. Heron's formula suppose triangle 2 is an isosceles triangle with the same base as triangle with perimeter P and area T2. Theorem 10a guarantees that area T2 is greater than T. Since triangle 1 and triangle 2 have the same base and are both isosceles, this implies that the perimeter P of triangle 2 and hence of triangle is larger than triangle 1. This is where that triangle be any triangle with area T and perimeter P. Suppose triangle 1 is an isosceles triangle with the same base and area as P, but with perimeter P1. We shall prove that P is greater than equal to P1 with equality only if triangle is isosceles. Isosceles is that 2 sides are equal, and according to them being rigid, that means that they'll always be symmetric and congruent their opposite angles. See, Theorem 11a. Of all the triangles with a given perimeter, the equilateral triangle has the greatest area. And so what he does, he presents 3 proofs, each with its own merits, ... Simon Lewillier's, follows the method of successive approximations. Here we might frame it that it's described first kind of like this fundamental approach from the spiral space filling curve, making geometry already. It's isoperimetric. Kind of trivially, and not that's necessarily well founded, but it does provide a lot of things. And then what's so key about it is that these other things that so arise from it are so related these ways. It's Euclidean. Conduct an infinite sequence of triangles. Also, our triangles become more and more nearly equilateral. So he's established this system of these inequalities and showing via the properties about the angles and their congruence and their equality. That all he needs to do is show that the sides become equal or the angles become equal, and that's the same thing. Is so for concave, is so for convex polygons that if their side lengths are equal to each other and it's convex, it's regular. It's like so. But I haven't found yet where does this harmonic mean. There might be several chapters down. So theorem 11b, of all the triangles with a given area, the equilateral triangle has the least parameter. Isoperimetric theorems for polygons. To quadrilaterals and polygons in general, for brevity, we call a polygon of n sides an n-gon. Regular n-gon is an n-gon with equal sides and equal areas. So for trigonometry, the idea is to figure out n-gonometry. But then the idea is that for trigonometry, it also can also be written as trilateralometry, which is where you take, instead of that the right triangle makes for Pythagoras the computation of sine and cosine according to the value of the hypotenuse and then the value of the coordinates, that sine and cosine are those coordinates, their values, to compute the value of sine and cosine, these complementary functions that, there's orthogonal functions, when you take the product of them for a given value and you take its integral, it equals 0, and when you take the integral of one or the other times its weighting function, it equals 1, and that thusly, among other kinds of orthogonal functions, that being the property of being orthogonal, a pair of functions, that they establish all these kinds of transforms that you can then thus separate systems of equations in terms of one or the other, in terms of the parameters left and right, and so then that way then they can be solved. It's pretty cool. Then the other idea is that you take an equilateral triangle and you set it as upon a line, and then you unhinge one of its vertices, and then you evolve the two sides not on the line and trace out the end point as each of the hinges open at the same rate until it's a flat line. Then you flip that over, and then you kind of fold back up the box, or fold it back as an underline. And in this manner, what you arrive at is that it's traced out the sine curve. Trilateralometry. Then also the idea is that whatever a square does, or any other regular polygon, unhinging one point, holding that one on the line, rolling it out till it's flat, flipping it over, rolling it back up, and lateralometry. which has the greatest area? Circle. He says it's regular. It's theorem 12. Of all n-gons inscribed in a given circle, the regular n-gon has the greatest area. Now, again, I might have any mistakes from my own, and secondly, when I leaf through this, I might have kind of picked this up subconsciously, but otherwise, it's just it was already mutually understood between what I understood and what Kazarinoff explains in details and proves. That then knowing various of these theorems from the middle sometimes is better than knowing the theorems at the beginning and end, because they provide a framework to build up or down from them. They have to be built up to them to arrive at this middling kind of theorem, but later with that kind of theorem, then it becomes easier to prove either way, these things. So it's described that in terms of chords, arcs and chords, that for a given slice off the circle, that a polygon fits in that, and then it's shown that the angle to fill it up and to have the most area out of that would be in such a manner as to make it so why there's not any polygon that has more area than a circle does for its arcs and chords. Of all quadrilaterals with a given area, the square has the least perimeter. It's most regular, and it's kind of already established. But then he has there's some other proofs that are just more particular and relevant and direct from the properties of the square, or the properties of quadrilaterals, rectangles. Given any n-gon which does not have all its sides of equal length, one can construct another n-gon with the same perimeter, with all sides of equal length and with a larger area. So again, this is just a corollary of one of these other theorems, and so described a little bit. The regular n-gon has the greatest area of all n-gons with equal sides and the same perimeter. Another theorem which we cannot easily prove is the regular n-gon has the greatest area of all n-gons with equal sides and the same perimeter, that it's convex. Because if it's concave, then it can basically dent in and have much less area. So the author does not, I haven't seen the words concave or convex, so I don't know if it's included in these definitions. And then he talks about Steiner's attempt. Well, I've been talking for a while. Thanks for listening. It's just meant to be easy listening, and then for the mathematical content, which I always try to be correct, and if I ever make an actual mistake and I later figure it out, I retract it in a sense, or fess up to any errors, mistakes, so I don't, because I like to be right, and that's one way to consider why it's psychologically reasonable that I study mathematics so much, is because I really feel like then it's the greatest way to be the most right. So then it can at least be easily understood that why that is so, and it's not because I'm selfish, but it's also just a way to look at that. Then you can say I can see why he feels like that it's relevant to then that is establishing this conscientious formalist 24/7 approach to rigor and formalism and constructivism for its own sake, and also to not be wrong, and to consider foundations and all this stuff. It's just especially to that's the reason, and anybody else could have that same reason, so I'd consider that psychologically fair, So here he gets into some more of the description of the historical accounts of the well-known and explored theorem proving that goes on in this milieu about these isoperimetric theorems. We haven't quite got to the harmonic theorem, so I guess we'll be continuing until we get to the harmonic means later. Vis-a-vis, as we've been discussing here and considering and researching and exploring and explaining as of the fundamental theorems and explaining as about the deconstructive accounts, which offer alternatives to some of the uniqueness results for these singularities in the theories that result multiplicities in the theory, that the harmonic functions are described those whose Laplacian is 0. And then it's described sometimes, well, our theory of potentials is a harmonic function theory, and then it's about the Dirichlet problem and this and that. Here it's described various alternatives to get up to and arrive at that. So for this book on the relations that reflect for orderings for any two elements, the trichotomy is established, GT, LT, or eq, or not equals, or GTE or LTE, those being letter initialisms or acronyms for the usual signs, Harriot's and this and that. I'll continue at a later date. If I recall, in arithmetic, we were introduced to the laws of equality and inequality. And so the greater than or less than sign were explained this way. And so this would have been in kindergarten or first grade. And we'd have this series of instructional multimedia type of presentations. So back in the day, that would have been like a slideshow with some sound to it or something like that. Or maybe like some posters and a story or something. So anyway, it was these ants and these ants, and so they had this every day or so for quite a while, and it lasted a couple of weeks for the math section of the class that day, and it was these ants, and they went on this adventure through these valleys and stuff like that, and I forget all about it, but I was like, yeah, I learned something about it, but then they had a story too. I'm like, I don't need a story. This is just learning. So anyways, one day the teacher was instructing us, and she said after greater than or less than, it says two numbers are greater than or less than, and well, how can you tell? Because it looks like the diminuendo and a crescendo, which is like it goes from less to more or something like that, and which I learned later. And so then for Harriot's, these are like left and right angle bracket, because then they're also used as paired brackets, indicating also directionality and grouping inside in linear notation. So the idea is this, is like she said, think of the symbol as an alligator, and it's the alligator's mouth wide open. And it always is going to eat the bigger number because alligators are greedy. And I was like, well, I could see that going either way, But in this case, the small fish eats the big fish. And whereas there's a usual notion that the big fishes eat the small fishes until finally the big fish dies, and then he decomposes and starts back from worms and stuff. Now, that's a little bit more gruesome and graphic, but anyways, this idea of a mnemonic or a thought device or how to remember something was established that long after I forgot most of the rest of the time in those classes, that lesson sticks out as less useful than except as an object lesson of not an object lesson. But anyways, the ants are pretty cool. Hey, well, have a great day, and that's a traditional goodbye. So goodbye. Thanks.